In 2012, two consumer graphics cards designed to run video games trained the neural network that shocked the field of artificial intelligence. But the decision behind that moment happened 6 years earlier, when NVIDIA quietly released a tool the market barely noticed. How a gaming company came to dominate the AI revolution starts not with intelligence, but with 3 engineers and a booth at Denny's. On April 5th, 1993, Jensen Huang, Chris Malachowski, and Curtis Preem officially incorporated NVIDIA. The 3 engineers met at a Denny's in San Jose, drinking coffee and mapping out a business plan for a market that was still in its infancy. Huang was a veteran of LSY Logic and AMD, while Malachowski and Preem brought extensive engineering experience from Sun Microsystems. Their collective mission was highly specific: to accelerate graphics-based computing for the personal computer, designing dedicated hardware that could handle complex visual data at unprecedented speeds. In the early 1990s, PCs were mostly text-based, utility-driven machines. Visual computing and 3D graphics were niche, expensive luxuries. The founders bet that video games would become the commercial engine to fund the massive hardware development required to change this. They focused entirely on solving a single, complex mathematical challenge: how to render millions of polygons on a consumer screen in real time, simulating 3-dimensional depth on a flat monitor. This singular focus on gaming defined NVIDIA's early identity, anchoring its survival and reputation to the PC graphics market, where they fought for market share against dozens of now forgotten rivals. At the time, the idea that a startup dedicated to making video games run faster would eventually build the infrastructure for global artificial intelligence was unthinkable. Yet, the mathematical physics required to render virtual light and shadow would ultimately lay the groundwork for a far vaster computing transition. In November 2006, at the Supercomputing Conference, NVIDIA announced a technology called the Compute Unified Device Architecture, or CUDA. It was a software platform and programming model designed to unlock the graphics processing unit for general computing. For over a decade, the company had built chips optimized to render 3-dimensional virtual worlds. To do this, these processors use thousands of simple cores working simultaneously, processing millions of pixels at the exact same time. This parallel architecture was fundamentally different from the central processing unit, or CPU, which relied on a few highly powerful cores to handle tasks one after another, like cars navigating a single-lane highway. NVIDIA engineers, including chief architect David Kirk and software lead Ian Buck, realized this massive parallel structure could do far more than calculate light and shadow. If scientists could program it, a desktop could deliver the power of a supercomputer. CUDA provided that bridge by introducing a C-like language, allowing developers to write software directly for the silicon's parallel processors. Internally, it was an expensive gamble. NVIDIA had to redesign its hardware lineup to support the platform, adding significant cost to chips destined for a consumer market that still only cared about video games. Wall Street largely dismissed the move, viewing it as a niche experiment for academic researchers. The world barely noticed that a gaming hardware company had just written the code for a much vaster computing market. In September 2012, a team of researchers at the University of Toronto entered an annual computer vision competition called ImageNet. Alex Krzyzewski, Ilya Sutskever, and Jeffrey Hinton submitted a deep neural network named AlexNet. To train this model, which contained 60 million parameters, the team did not rely on traditional central processors. Instead, they used two consumer graphics cards, the NVIDIA GeForce GTX 580. The cards, each equipped with 3 GB of memory, ran custom code written directly in CUDA and C++. This software, called CUDA ConvNet, allowed the network to process millions of pixel calculations simultaneously, reducing a training process that would have taken weeks on traditional CPUs to just 6 days. When the results were announced, AlexNet dominated. The system slashed the top 5 error rate from 26% to 15.3%, an unprecedented margin of victory. The computer science world took notice. The breakthrough proved that deep neural networks, long dismissed as computationally impractical, could be trained at scale using parallel processing hardware. For 6 years, NVIDIA had manufactured CUDA-enabled chips without a clear mass market application. Suddenly, academic labs, technology firms, and researchers realized that the exact hardware they needed to power the deep learning wave was already sitting on retail shelves. The hidden software ecosystem NVIDIA built had just matched the exact requirements of a new era of computing. The question now was how the company would handle a sudden, massive surge in demand once the entire industry realized the true value of this hardware. In the years following the deep learning breakthrough, the demand for parallel processing hardware shifted from university research labs to the core infrastructure of the global tech industry. Major cloud providers and artificial intelligence laboratories began purchasing these processors in unprecedented volumes, integrating them directly into the servers powering the modern internet. NVIDIA was no longer simply selling graphics cards to PC gamers. By the early 2020s, the company's business model had fundamentally flipped. During fiscal year 2022, data center sales grew to represent 48% of total revenue, officially overtaking the legacy gaming business for the first time. The transition only accelerated. By fiscal year 2026, data center operations generated nearly 90% of the company's revenue, pulling in tens of billions of dollars each quarter. This commercial scaling drove historic financial outcomes. NVIDIA's market capitalization, which hovered around $30 billion in 2016, climbed past the $1 trillion mark in 2022, eventually exceeding $2 trillion by 2024. During the first quarter of 2026, the company reported $68 billion in quarterly revenue, maintaining gross margins above 70%. NVIDIA had moved from a hardware supplier to the essential infrastructure layer of a global technology transition. With its software and silicon integrated into nearly every major data center, the company had secured a dominant market position. Yet, a lead of this magnitude inevitably invites intense competition. The question was, who could realistically challenge a monopoly this absolute? The response to this dominance did not come from traditional chip makers trying to build better graphics cards. Instead, it came from NVIDIA's own largest customers, who chose to design their own hardware. Google bypassed general-purpose processors entirely to build the Tensor Processing Unit, called TPU. Engineered specifically for the matrix multiply mathematics of deep learning. These custom chips now power Google's Gemini models and offer cloud customers an alternative that avoids the high price premium of NVIDIA hardware. Amazon followed a similar path, introducing Trainium as an efficient, cost-effective accelerator tailored for large-scale model training within its AWS ecosystem. At the same time, geopolitical forces introduce a different kind of friction. United States government export controls, tightening through 2025, barred the sale of advanced AI semiconductors to China. This trade wall stalled shipments of NVIDIA's premier chips to a market that historically generated a substantial share of its data center sales. In the vacancy, Chinese domestic suppliers like Huawei began deploying local silicon to power domestic AI clusters, accelerating a shift away from American hardware. While these pressures do not erase NVIDIA's current dominance, they introduce new limits to its growth. The core question remains unanswered. Is the platform NVIDIA built a permanent, structural monopoly that will anchor the next generation of computing? Or does its current dominance represent a temporary lead, captured by a gaming company that simply had the right hardware at the exact moment the world changed? Today, NVIDIA's hardware underpins the global expansion of artificial intelligence. Yet, as competitors build custom silicon and geopolitical borders tighten, the landscape is shifting. The question is no longer how one company built this foundation, but whether anyone can maintain a monopoly over the computing power of the future.